Okay, jumping back up to chapter 9 to finish off our periodic table trends. Last time we were in chapter 9, we talked about ion size. We also talked about atomic size. So for atomic size, let's see if we can find the slide. Our trends for atomic size when we were moving down a column, every time we move down a column, we're adding on a new shell to whatever our element is. That's going to make it bigger. So moving down, we're getting bigger. And when we're moving across the period, so left to right, across a period, we're increasing the effective nuclear charge, that's a ZF, but we've got the same size shell. So we're jacking up the positive charge in our nucleus, and that's going to cause those outer electrons to get pulled in slightly as we move left to right. So it's going to get smaller left to right, which means it gets bigger right to left. So for atomic radius, our size increases when we're going down a column and when we're going to the left along a row or a period. For ion size, we're changing the number of electrons that we have. Also going to stop here briefly and remind us that diamagnetic and paramagnetic are important concepts. Paramagnetic means we've got unpaired electrons. Diamagnetic means we've got all paired electrons. For our ionic radius, cations are small because we're removing electrons from the outside. So that's going to cause it to get smaller. Our anions, our negatively charged ions, are bigger. So if it's a positive ion, it's going to be small. It's going to get smaller. If it's a negative ion, it's going to be bigger because you're adding on extra electrons. We also looked at isoelectronic ions where they had the same number of electrons, and the rule was the same. Negative ions are going to be bigger. Positive ions are going to be smaller. So we're looking at size on this top row here. I don't know why it's not labeled. Or radius. So notice that our S2 minus, our Cl minus, our K plus, our Ca2 plus, these all have the same number of electrons. These all have 18 electrons and different numbers of protons. Notice that our negatively charged sulfur, it's got the biggest negative charge, it's got the biggest size. Chlorine's a little bit smaller, 3 picometers smaller, and then our positive ions are significantly smaller. So negative ions are bigger, positive ions are smaller. That was our first-ish trend. Question?
I was just wondering what the PM stood for on the chart.
PM is picometers. P is the prefix for pico. I've got a really bad salsa joke that's related to that, but I'm not going to tell it right now. Okay, another trend that we have is ionization energy. And ionization energy is the energy that it takes to form an ion, but specifically to remove an electron from the atom or ion in the gaseous state. This is always going to be a positive number. It always takes energy to remove the electron. You have to put energy in to remove an electron. And we have a couple of different ionization energies. You probably saw ionization energy if you've taken Chem 20. We only talked about, in Chem 20, at least in my classes, we only talked about first ionization energy. We're also having a conversation now. We're going to add in second, third, fourth, etc. ionization energies. So our IE1 is our first ionization energy. The 1 means that it's our first one, and that's removing an electron from the neutral atom. Our IE2, this 2, means that it's our second ionization energy. So after we've already removed one, now how much energy does it take to remove the second one? And the idea continues for our third and our fourth, and so on. So our first ionization energy decreases going down a group. So when we're moving down a column on our periodic table, the energy decreases. This makes sense if we think about it from the atomic size perspective. When we're going down a column, it's getting bigger. The electrons are getting further and further away from the nucleus, where all the positive charge is in the center. So it's going to be easier to pull off those electrons because they're not held on as tightly. So they're not held as strongly. The opposite is also true. It increases, ionization energy increases as you move up on the periodic table because we're getting smaller and smaller. So the electrons are closer to the nucleus, and so they're going to be harder to remove. Our first ionization energy generally increases across a period. So left to right, we're going to see an increase in our ionization energy. Generally, this applies really well for our main group elements. For our transition elements, they're a little bit wonky. They were also wonky with atomic size. They were just kind of the same when you moved left to right, and it really only changed for atomic size when you moved up and down. So it's increasing across a period, again, because we're increasing the effective nuclear charge, and so the electrons are held more strongly. Also going to point out that our trend for first ionization energy is opposite of our size trend. So if you really want to do the least with memorizing, you don't want to memorize the concept at all, you just want to memorize arrows, it's just the opposite of atomic size. So if you memorize atomic size, just remember that ionization energy is the opposite. That's for first ionization energy. And notice that our noble gases here have the highest ionization energies. They've got their full and complete outer shells, so they really don't want that to get broken up. They're very stable with their complete outer shell. Here's a three-dimensional graph showing our ionization energy. So we've got just our periodic table on our x and our y, and then our z-axis, the height of these columns, is the ionization energy. So helium is by far the tallest, neon is a close-ish second, then fluorine. Generally, it's increasing towards helium. So based on our periodic trends, we want to determine the element in each of these pairs with a higher first ionization energy, if that's something that we can actually compare. So first up, we've got tin or iodine. So they're in the same row, so we're comparing left and right. Which direction does our ionization energy increase, left or right? It increases to the right, and so iodine is going to have the higher ionization energy. We've got calcium versus strontium, which is going to have the higher ionization energy. It's going to be calcium. Ionization energy increases up a column. Carbon or phosphorus, we're looking at C or P. This one is sort of like not entirely sure. I'm going to guess that it's probably carbon. But for this one, we've got conflicting trends. I'm just guessing that the size difference from moving up like taking off an entire shell, is probably going to be a bigger factor than the little bit of compression that we get from increasing the effective nuclear charge. This one we've got conflicting trends, though. Don't expect to see something like that on an exam. And then we've got fluorine or sulfur. Which one's higher ionization energy? It's going to be fluorine for sure. It's both one row up, and it's also one spot to the right. So those are additive trends. There are some exceptions to our trends for first ionization energy that I'm not going to worry about. Yeah.
I have a question about the valence electrons. You said they'd be farther away from the nucleus, and then when they're farther away, does that mean the electrons are closer? That's what you're saying?
Farther away means they're farther. So they're valence electrons are our outermost electrons. So the further they are away, the easier they are to pull off. So the lower the ionization energy is going to be. So that's why the ionization energy decreases when you move down a column. It increases when you move up a column. Because when we're moving up a column or a group, they're getting smaller, so the valence electrons are closer. When we're moving down a column, we're adding shells every single time, so they're getting further and further away. That's why it decreases. So first ionization energy generally increases left to right. There's an exception between our 2A and 3A groups. This has to do with the difference in the energy of the electron. So boron loses a 2p electron versus beryllium's losing a 2s electron. So a 2p electron is easier to remove. It's higher energy. Another exception is that nitrogen has a half-filled shell. Half-filled shells are going to be especially stable. Oxygen has a singly paired electron, so that's going to be a little bit easier to remove than we would expect. I wouldn't worry too much about those. We also have, for successive ionization energies, each additional electron requires more energy. So when you remove one electron, you're increasing the effective nuclear charge. We get less shielding because now we've got one fewer electron. That higher effective nuclear charge means our electron's closer to the nucleus, means it's harder to remove. There's also a large increase when the first core electron is removed. So after all valence electrons are gone. So if we look at sodium, its first valence electron is its only. So it's got a relatively low first ionization energy. Right? It's in the 1A group. When you remove that one valence electron, now it becomes like a noble gas. So we've pulled off that outermost shell, and now it's got a completely filled shell underneath that. And so we see a giant spike in our ionization energy between our first and our second for sodium. So that first ionization energy is going to be our 3s1 electron. For our second ionization energy, now we're removing from a 2p ionization energy. So we're now removing from a core electron. Those core electrons are a whole shell closer. We've also changed our, actually this shouldn't affect our effective nuclear charge, but we're now breaking up what's effectively a noble gas. For magnesium, magnesium is one spot over from sodium. So both the first and second ionization energies are going to be our 3s electrons. We're plucking off our 2 valence electrons. And then our third ionization energy, we see a massive spike because we're taking off our first core electron. And if we look at a table of our elements versus their ionization energies, so as we're moving down here, sodium, magnesium, aluminum, we're moving step by step across our periodic table. So for valence electrons, one, two, three, four, five, six, seven, 8. So one valence electron means for sodium we can remove one relatively easily. The second one is our core electron, so we see a giant spike. Magnesium we can remove 2 with pretty decent increases. We see a giant spike for our third because that's our first core electron. And the same trend all the way down. Our first core electron does not want to come off. So we're going to see a massive spike in ionization energy for all of those. So ionization energy increases so much for the first core electron. So our valence electrons will see a successive step up in terms of the ionization energy. When we get to that core electron, it goes through the roof. Absolutely massive spike for our core electrons. That's kind of the only trend for our IE2, IE3, etc. stuff past our first ionization energy. We've still got 2 more trends. So we've also got electron affinity. Electron affinity is our energy change when we gain an electron. So this is sort of the opposite of ionization energy. Ionization energy, we're removing an electron. Electron affinity, we're adding an electron. Ionization energy, removing an electron. Electron affinity, adding an electron. Electron affinity is usually negative. So for ionization energy, these numbers are all positive. You have to put energy in to remove the electron. Electron affinity is usually negative. When you add an electron, you get energy out most of the time. Some alkaline earth metals and all noble gases have positive electron affinity, meaning you have to add energy. They don't just willingly accept gaining an extra electron. Any ideas why that would be? What column is our alkaline earth metals? It's the second one. So beryllium, magnesium, calcium, etc. What do those have in common in terms of their electron configuration? These are going to have 2 valence electrons. So they're going to have NS2, which is a full S subshell. So where does the next electron go? What comes after S? P. And this P subshell would be empty. So we're putting it into a much higher energy level subshell. So that would explain why this electron affinity would be negative, or positive, sorry, because we're putting it into a much higher energy bracket. So it's going to take a little bit more energy to do that. Our noble gases are also going to have positive electron affinity. Our noble gases have full valence shell. So our next electron goes into n+1 s. We're adding a brand new shell to make that brand new shell a brand new home for our electrons. We've got to put all the energy and resources in to build that. For electron affinity, for our alkali metals, our first column, sorry. Group 1A, when we're going down group 1A, electron affinity is more positive. Which is a decrease because these are negative. Because electron affinity values are negative. It's very fun and not at all confusing getting to deal with negatives. Electron affinity generally increases or becomes more negative across a period. So generally, electron affinity increases, the number gets bigger, up and to the right. With some exceptions. For our group 5A, we get a lower electron affinity than expected because we're going from up, up, up to up, down, up, up. The electron that we add has to pair, and that's not very nice. Our groups 2A and 8A have very low or positive electron affinity values because the added electron goes into a higher energy level or sublevel. You don't have to copy all this down. This is so that you can maybe see what we mean by this. It's more for future you. The highest electron affinity for any period is going to be the halogens. Halogens really want to gain one electron. That's why they form negatively charged ions. So they're going to have the most negative values. So our electron affinities. For 1A, our number is increasing. It's becoming more positive, which is a decrease in electron affinity. Fun and not confusing. When we're going down, so number gets bigger as we go up. Number gets bigger as we go left to right, generally. There's lots of exceptions. So I would say just remember it in the generally sense. As a reminder, we've got generally two major classes, and then like a weird zigzag line, two major classes of types of elements. We've got metals, and we've got nonmetals. We also have the metalloids or the semimetals that live on that zigzag line from like boron to astatine, sort of. But generally speaking, metals and nonmetals. Metals tend to do things that we know that metals do. They're malleable and they're ductile. You can bend them into different shapes. You can pull them into wires. They're shiny, they're often lustrous, they can reflect light, they conduct heat and electricity. They form cations in solutions. They lose electrons in redox reactions. Nonmetals tend to be brittle, dull, non-reflective. They're insulators. They form anions, and they tend to gain electrons in reactions. Where on the periodic table do our metals live? Where do our metals live? They live down and to the left. Where do our nonmetals live? Up and to the right. So generally, metals are down there, and nonmetals are up there. The reason that we're talking about this, the reason that I'm pointing this out, because our last trend is metallic character. How much of a metal is it? Motorcycle going brap in the background. So metallic character is how much of a metal are you? How much like a metal is it? And our metals live where again? Down and to the left. And our nonmetals live where? Up and to the right. So up and to the right, not very like a metal. Down and to the left, more like a metal. That's the whole trend. That's it. That's the whole trend. The further to the left it is, the more of a metal it is, because our metals are to the left. Our nonmetals are to the right. Our metals tend to be down. Our nonmetals tend to be up. So metallic character increases to the left and down. We had another trend. We had another quantity that had the same trend. It's the same as atomic size. Okay. Some trends before we wrap up. We've got GE or SN. GE, SN. Which one is more of a metal? SN. SN's more of a metal because it's further down. Also, with this periodic table that we have, right, we can see the metals. Tin's a metal, metalloids. Germanium is a metalloid. So obviously tin is more of a metal. We've got GA or SN, so SN showing up again. We hit the shrugging emoji. We've got conflicting trends. I would guess that it's tin just because it's further down. I don't know if that's actually true. That would be my guess, is that it's probably tin. You won't get questions with conflicting trends if you get trend questions. And then we've got phosphorus or bismuth. It's going to be bismuth because it's further down. And we've got boron and nitrogen. It's going to be boron because it's further to the left. It's more to the metals side. And then a summary. table for all the different periodic trends and some reasons for them. So this is a great summary slide. This is one of the tables from the book.